Hi, I'm going to show you how to use conservation of momentum to solve a problem. So the physical situation is this, that we have a person sliding across on ice and they throw a ball. Okay, and so we need to have some data to make a prediction. So we know that the person has a mass, we call that mass 1, of 80 kilograms. We'll say that the ball has a mass of 5 kilograms. Well, let's say that we know what the velocity is before the person throws the ball. So they're sliding along. We'll call that V initial, and we use the subscript x to indicate that they're moving horizontally, and that is 3 meters per second. Okay? And when the person throws the ball, the velocity of the ball, so the velocity of the ball, we use subscript 2 for the ball, final, meaning after they throw it in the x direction, is 10 meters per second. And the goal here is to find out how fast the person is moving and in what direction after they throw the ball. So again, person sliding along on the ice at 3 meters per second, carrying a ball, and then they chuck the ball forward at 10 meters per second. How fast is the person going after they do so? Okay, so what the first thing we need to do is figure out what law of physics we're going to use to describe this physical situation, to actually to model it. So the reason that I could drive this problem with ice is because we need the physical situation to be no significant net external force. Okay, of course there are forces on both of these objects. If this occurs on or near the surface of the Earth, there's a weight force down, there's a normal force up, but there's no significant net external force on the system. So we can use conservation momentum, and conservation momentum, written very concisely, is this. So summation of P initial equals summation of P final. So P is the symbol for momentum. It's a vector. It has a magnitude and direction. In one dimension, you just need to keep track of your pluses and minus signs, and it's fairly straightforward. So this is a one-dimensional situation with two objects. So I'm going to write down conservation momentum for that situation. So mass 1, velocity 1, initial x. Okay, so 3 subscripts often in momentum problems. You have which object you're talking about. You have, is it before or after this interaction? And then you have whether it's x, y, z, or whatever. Okay, so I've got to be careful with those subscripts. They're not just decorations. Okay, and then I just change the i's to f's. So mass of 1, velocity of 1 after the person throws it, and then mass 2, velocity 2 after the person throws the ball. Okay, so I'm going to try to simplify this a little bit. So you'll notice that this only has 2 subscripts. So before the person throws the ball, they're just sliding along together with a common velocity. So in this case, there's no distinction. And so really, this left-hand side of the equation becomes the sum of the masses times the collective velocity. I think that makes intuitive sense. The momentum of that group is the collective mass times the collective velocity. The right-hand side remains the same, though, because there's we can't simplify any of these terms. So the goal here, as I said before, is to solve for the velocity of the person after they throw the ball. So we just have to grind out some algebra, start ripping things away from this term, and then we'll throw in the numbers. So I'm going to skip over the algebra here. So V1 final x will be this. Okay, you can check this yourself if it bugs you that I'm skipping steps. Okay, so there's the symbolic solution for the velocity of the person after they throw the ball. Let's throw in the numbers and find out what happens. Okay, testable prediction using a law of physics. So mass 1 of 80, mass 2 of 5, initial collective velocity of 3, subtracting off mass 2, which is 5, times its velocity after the person throws it, and then mass of the person is 80, and I throw that into my calculator, and it spits out 2.56 meters per second. Okay, so that's testable prediction. We predict the person slows down from 3 meters per second down to 2.56 meters per second after they chuck the ball forward. Okay. So that's it. Thanks for watching.